Recall that a upper gradient of a function u is a Borel function so that the integral along path is larger than the difference of the u values at the two endpoints. And the Newtonian Sobolev functions were those functions for which u itself belongs to Lp of x after we introduce a measure on the space. And there exists some upper gradient g of u so that g also belongs to Lp of xu. If this is true for a function u, then we say u belongs to the space n1p of xd and mu. Now, one of the promises that we had made about Newtonian Sobolev functions was that they would be absolutely continuous along path. So we have previously talked about definition of what it means for u is absolutely continuous on a rectifiable curve. Above also the curve was assumed to be rectifiable so that the integral is defined. Now, one of the lemmas that we had was that if g is an upper gradient of u, we don't even assume at this point that g is in Lp, and gamma is a rectifiable curve such that integral over gamma of g is finite, then u is absolutely continuous on gamma. So this observation was motivation behind many things, including maybe definition of upper gradient as well. But here is the question. If we go back to the definition above, we only require this inequality, which in some cases, as we have seen in examples, will necessarily sometimes be infinity. So all we need is that this holds and that g globally belongs to Lp. There is no mention that integral of g along any curve is finite. So per definition, we don't a priori know whether integral of g is actually finite on any path. And we will see that it's not always true that it's actually finite on every path. However, for nice spaces, we want to be able to make the following claim that if u is in n1p, then integral of u along gamma is finite for the part that we need to make precise for almost every curve. And from which it would follow that u is absolutely continuous in almost every curve. But what is this notion? What does it mean to talk about almost every curve? Or in other words, what does it mean to say that a certain class or subcollection of curves is negligible? And the notion of modulus of path families is precisely answering that question. The notion comes originally from complex analysis, has had many applications in many other areas, especially the study of conformal functions, because it's a conformal invariant, and also quasi-conformal maps in abstract settings. Actually, one of the definitions is based on the very notion of modulus of path families. But let's see what that is. So we begin by talking about admissible functions for a collection of paths. So a path family is just a bunch of curves in a space. They don't all have to be rectifiable, by the way. So we say a function rho, Borel, is admissible for a path family gamma if integral over gamma of this function rho ds is at least 1 for every gamma from my collection that is locally rectifiable. So this integral will make sense if we have locally rectifiable path, and we don't have to worry about non-rectifiable path in this collection. So if rho is good for all locally rectifiable ones inside this class, then it's good for the whole family. Example is that this family, the class of, there might be no such actually rho. There might be no such rho. For example, if gamma contains a constant path. So if you have a constant path, a path that just doesn't move, then this integral rho ds will be necessarily 0, even if you let rho be just constant infinity. And there is no way you can just make it bigger than 1. So in this case, the class of admissible functions will be the empty set. So now that we have this class of functions that charge our curves, comes the definition of the P modulus, to be precise. So the P modulus, where P is a number, a positive number, so the P modulus of gamma is, among all admissible functions, you try to look for the ones with the smallest p integrals. So d mu over the whole space x. Okay, so it's this infimum where inf is over all, of course, admissible functions for gamma. And we agree that infimum of empty set is infinity. So, which is consistent convention in many situations in analysis and geometry. Here it simply says that you cannot achieve what you want, which is charging all the curves to at least 1. If you cannot do it, that means, well, the family is kind of not manageable, and that's why then the modulus is infinity. So this we denote by mod p of gamma. If you've read complex analysis settings, there is no mention of p because the natural exponent is 2, so it will be just mod or 2 modulus because we're in the plane. Okay, so looking at these two conditions together, being admissible and this one, the modulus is trying to say how much do you need to spend in terms of LP energy to be able to charge all the curves, to be able to get enough density along every curve from your family. So, and if we continue the definitions, so we say a certain property, so some statement, some claim, some property holds for P almost every curve in a space if the P modulus of curves for which it doesn't hold, So let's look at the bad collection of curves where this property doesn't hold. Is 0. So that collection is small from the point of view of modulus. So this will be our kind of the for okay, I was reading this as phi and I was like, where did that come from? So the notion of almost every curve, or more specifically p almost every curve, will be for us this one. And later we will see lemmas and results making this statement precise, that if you have a subtle of functions, then it is its integral along path is finite for almost every path, from which, as I said before, that it follows that then it is absolutely continuous on almost every path. So let me give you some, again, examples to give some meaning to this modulus. It initially looks very abstract. Let's talk about the planar case again. Take a rectangle. Let me make sure that the sides are parallel. And suppose this side is has length A, and this side has length B. And let gamma be path joining, so say left edge to the right one. So a path is a continuous function without loss of generality from 0, 1. So you can say that a path joins them means at 0 you're along this edge, and at 1 you end up here. Of course, there are much crazier paths that I cannot even draw. So let's look at this huge collection of paths. It's a very nice and doable exercise at graduate level from Fubini's theorem that the 2 modulus of this path family is A over B. In the function rho, the admissible function that realizes this, so to see that the modulus is less than this value, you simply take any guess that works. So if you take the constant function rho, which is 1 over b on the triangle, on the rectangle, and 0 outside, then if you integrate any path, because the path has to have length at least b, when you multiply into this rho b, you will get at least 1 in the integral, so it is admissible. And then when you take the L2 norm of that in R2, you will end up with A over B. So this shows that the modulus is less than A over B. But to prove that it's at least for any other admissible function you won't get further down, you need to apply Fubini's theorem. Some observations that follow from this is that larger A implies larger modulus, because in this case you get just more curves. So if you add to the list here, you just get a whole bunch of more curves, and more curves means bigger modulus. So modulus is a measure of how much curves you have, how many curves you have. But that's not the whole story, because you can now fix A and make B bigger or smaller. And in this case, you see that modulus goes up if B is short. So the shorter B becomes, it's more difficult to obtain this integral rho at least 1. Well, the area also shrinks, and so this is true only for 2 modulus. So if you work with a different P in this case, Not all of these will necessarily be true. So smaller b, which means shorter curves, implies, again, larger modulus. This is a general, true in more generality, and one way to make it precise is that if you have a gamma prime, so that every curve in gamma prime is a subcurve of a curve in collection gamma, then the mod of gamma prime will be at least as much as mod of gamma. So if you take subcurves, you take shorter curves, and then the modulus goes up. Example 2 will be very key and important example is the annulus. And that is in the plane you take, well, two concentric circles, hopefully, more like oval. Okay, now accept it as an annulus, so same center, different radius. And if this is bigger radius is r and this one is little r, then modulus, again, 2 modulus of all the curves that join the outer circle to the inner one. It can go outside and come back. It can do many much crazier things and join them. So this family will have a modulus which is okay, log of r over r and then 1 on top. Okay, in this case you see that, so this does depend only on the ratio of these things, so you can draw a much smaller annulus, but the modulus will be the same if the ratio is the same, so they might have same modulus. It only depends on the ratio, and also it doesn't depend on the location, which is less surprising because of all the homogeneity in the plane. And we see that if this little r goes to 0, it implies that the modulus does go to 0. And we can actually use this uniform bound in terms of ratio of annulus. I will actually show in a separate video that calculation. It's one of my favorite calculations. But philosophically, this means that if you let r just go to 0, then you're looking basically at all the path going through one single point. And the modulus of that is 0. This points in that direction, but we will give a rigorous proof later. So modulus of all gamma, that gamma goes through, say, origin, is 0. Because all the curves are required and restricted to passing through one single point, that kills the modulus. So one point can be really bad for, say, regularity of a Sobolev function. And this is actually happy news that if something fails at just one point, then we're not missing out too much. So the whole class of path going through that is negligible from point of view of modulus. And let me show you how important this notion is to complex analysis and how useful it can be. So example, there does not exist a conformal map between two annuli unless this ratio is the same for them. Or you can, the better one is when the ratio is equal, there is one conformal map, which is just scaling. So there does exist a conformal map between annuli if and only if this happens. So the proof, the easiest proof of this is that, well, if you have a conformal map, let's say a different size. If you do have a conformal map between here, this annulus, and here, and you first prove that this modulus is preserved. So being preserved means you have a curve family here, and then you compose with f. Each single one of them composed with f gives another family here. And it's easy to see that if you start with the family of all path as before, joining outside to inside, the image f of that curve family will be exactly the corresponding curve family here. Now modulus here is 1 over log r over r, and then modulus of f of gamma, which is modulus of gamma of this collection, is 1 over log r prime over r prime. And now that we know that modulus is equal to modulus, it's also not too difficult to prove if you know a little bit of complex analysis and linear algebra. It's just a change of variables formula using Jacobian. If you know this fact, then you see that f is conformal and this such conformal map exists if and only if these mods are equal, which means that r over r equals r prime over little r prime. So 3 very important examples already in the plane. The modulus of an annulus is given in terms of log of the ratio. Modulus of all path going through one point is 0. And then for a rectangle, the modulus is ratio of the sizes of the sides of the rectangle. To remember it, the more curves we have, the bigger modulus. That's why you put the a up here. So I hope this introduction to modulus was clear, and the definition is so metric that it does require nothing. Actually, we defined it on metric space. And yeah, we will continue to see what modulus does for us in the world of Sobolev functions. Thanks for watching, and see you in next video.